Hey folks, we've got one last section in this unit on hypothesis testing. It's doing hypothesis tests for proportions. So just like in Unit E, we talked about doing confidence intervals for means, and then we finished up by taking a look at confidence intervals for proportions. Here we're doing the same kind of thing. So we did hypothesis tests for means, mu, and now we're going to take a look at hypothesis tests for proportions, the binomial p. Write the classical approach, which is how we'll start here, and then we're going to do the p-value approach for this. Let's take a look at this particular problem right here. So a manufacturer contemplating a bulk advertising campaign has determined in order for the campaign to be successful, a response rate of at least 20%. So at least 20%, that's the standard that needs to be met, is needed. And so they do a pilot study. A pilot study is a sample. And we have an N here of 102, and the actual number that responded was 102, out of 600. So 102 out of 600 then. Test the null hypothesis that the population proportion that would respond is no less than 0.20. That's the standard that needs to be made. No less than is written like this then. So step number one, formulate the hypotheses, your HO and your HA. So HO is the standard that needs to be met here, that P is greater than or equal to 0.2, 20%, no less than 20%. The alternative is that we fail to meet the standard, so it's less than 20%. Step number two is to go to the flow chart. So let's go to the flow chart here then and see what we've got. And so I'm going to go back here to right there. Now, the top flow chart was for confidence intervals and tests for mu. We're going to be taking a look at this flow chart, which is confidence intervals and hypothesis tests for the binomial p, for proportions. There's really only two questions that we need to ask here. The first one is something that you've seen before. In order to do a normal approximation of the binomial in unit n, we said that n times p must be at least 5 and n times 1 minus p must be at least 5. Well, there's a difference between whether you're doing a confidence interval or a hypothesis test. With a confidence interval, there is no hypothesized value, so all we have is a p bar. So in that case, you use is n times p bar at least 5 and n times 1 minus p bar at least 5. With a hypothesis test, though, you're always doing the hypothesis. You're always testing it against the null hypothesis. So that's the p naught, which is in the null hypothesis. So instead of using the p bar, we use the hypothesized p value in the HO. Is p naught at least 5, and is n times p naught at least 5 and n times 1 minus p naught at least 5. If that passes, which is your check, and that's something I want you to see. I want to see you actually work through that. If that passes, then the only thing else that we ask here is capital N known? Do we tack on an FPC factor? So down here, if this were a confidence interval, we'd be on this side over here, but this is the hypothesis test. In our particular case, we didn't have a finite population correction factor, so we're going to be using formula number 5, which is this guy. If you take a look at this, you'll notice that in the denominator, we've got p naughts, not p bars, which is what we had in confidence intervals. So that's the only difference there between the two. Okay, so we're going to be using formula number 5. Let's go back to where we were. And so we've got Let's just show that check there here first of all. So check is n times p naught at least 5. And what we have is n is equal to 600. P naught is 0.2. And so that is, looks to me like that is 120. Check. And then is n times 1 minus p naught at least 5. And we've got 600 times 0.8, which is 480. Check. Check, check. We're good to go. There's no finite population correction factor, so we're using formula number 5 from the formula sheet, which is this guy right here. Okay? All right, let's go to step number 3. Determine the level of significance. If alpha is not given in the problem, then assume an alpha of 5%. I usually do that in step 1, but you can do that here. And then if you take a look then at the null and alternative hypothesis, what you'll notice is that the sign of the alternative hypothesis points down. So let's draw that out here as a picture. Again, on an exam, you could just simply put down the statement, but let's draw this out here. So here's a Z distribution. Whoops. Ooh, that's not very good. Well, close enough. Ah. All right. There we go. So what we do is we put the whole alpha of 5% in the lower tail here. And that critical value is minus 1.645. Let's go and see where we find that. So we can go back here to a Z table right here. And if we kind of flip this, think of this as being the 5%, although it's in the lower tail, then this would be 45%. If we look up 45% in the body of the table, we'll get 1.64, 1.65. It looks like it's about halfway between those two. Now, the reason why I've got 1.645 is because an alpha of 5% is very common, so we can just go to a T table. So let's go to a T table here. And remember that the last row of a T table are just Z values. So under the 5% column, we have 1.645. Of course, it's on the left-hand side, so it'll be negative 1.645. So there is our, here we are. There's our critical value there. So our decision rule then is if your Z star is less than minus 1.645, then we reject HO in favor of HA. Okay, the analysis is we take the sample. Remember, we haven't even seen the sample results up to this point. So now we take the sample. This is our P bar. P bar is equal to 102 over 600, right here, minus 0.2, and then in the denominator you use the P naughts. So P naught is 0.2 times 0.8 over 600, and that gives you a Z star of minus 1.84. Okay, let's just put that in green. Nope, that's not green. There we go. That is in here. That is in the critical region, the rejection zone. And so what we have here then is minus 1.84 is less than minus 1.645. Therefore, reject HO in favor of HA. The manufacturer's claim is probably incorrect. Manufacturer's claim. Sorry, this is the advertiser's claim, isn't it? Oh, well, the manufacturer of bulk advertising, that's what it is. Yeah. Okay, let's redo this problem as a p-value approach. And then I'm going to leave you with number 8 for homework. So let's take a look at this. Step number 1. Step number 1 was our hypothesis. Remember, in a p-value approach, it's exactly the same. So we said that p is greater than or equal to 0.2 against the alternative that p is less than 0.2. One thing that's really important to note here is that you're never testing p bar. Your hypothesis should never say p bar is greater than or equal to 0.2. Just like when you're testing mu, you never say x bar is greater than or equal to 1.6 or something like that. You're never testing your sample mean. You're using your sample mean to test your hypothesized mean. So it is a population parameter, a mu or a p. We're going to assume an alpha of 0.05. We could do that in step 3, I guess, but step number 2 is the same. We go to the flow chart, which I'm not going to go back to. That was formula number 5. And formula number 5 here then said that Z star is equal to P bar minus P naught over the square root of P naught times 1 minus P naught over N. Step number 3 is where we deviate from the classical approach. All we do at this particular point is put down our decision rule. If your p-value is less than alpha, right, that was 5%, then we reject HO. It's always the same for any stats problem on the face of the earth that uses p-values. It's always the same. The alpha might be different, but it's always, if the p-value is less than alpha, reject HO. That's the stats mantra. Remember that. Step number 4, Z star is equal to 102 over 600. Whatever that turns out to be, minus 0.2 over the square root of 0.2 times 0.8 over 600, and that comes to minus 1.84. So steps 1, 2, and 4 are exactly the same. When we come to step 5, this is where we say, all right, let's take a look at a Z distribution. It's kind of flat in there. It's probably not that flat. And we end up with minus 1.84. Let's put that in green here. Because the alternative hypothesis is pointing down, we're going to calculate the p-value from whatever computed Z star value we get down, even if it was a positive number. So on the right-hand side, we would still calculate it from that point down, because that's what the alternative hypothesis is interested in, that point down. So we're going to go back to a Z table and look up 1.84. And so that is back on, I think it's this page here. There it is. Okay. So we look up 1.84, and so here's 1.8, and then 4. Looks like right here, right there, is 0.4671. Now take a look at the picture at the top here. We have to flip it in our minds here, but we're interested in actually the equivalent of this area in the lower tail, right? So minus 1.84 is the same, 1.84 down is the same as positive 1.84 up. And this area here is 0.4671. So we're going to subtract that from 0.5. And that's going to give us actually our p-value. So our p-value will be 0.0327. So 3% in the tail. Let's go back to where we were. We're on the p-value approach. Here we are. So what we've got here then is that this p-value is 0.0327. So our decision then is that 0.0327 is less than our alpha, right, of 5%. Therefore, we're going to reject HO. Now, an important thing here in terms of the interpretation of the p-value. And the p-value, this is something that you really need to remember here, is the definition of the p-value. And that is that there is a p-value percent chance of getting a sample result this extreme. This extreme means different from the hypothesized value. So in our particular case then, what that means is there is a 3% chance of getting 102 out of 600. What are we measuring here? Oh, people who bought into the advertising campaign supporting the advertising. If HO is true, I should put down up here HO, the hypothesized value. If HO is true, i.e. that we are meeting the 20% threshold. Remember, we needed to have at least 20% acceptance. So there's only a 3% chance of getting these kind of results. I think 102 over 600 is about 17%. So only 17% of the sample actually supported the campaign, and we needed at least 20%. So the 17% is significantly lower. And so we would say that we reject HO in that particular case then. So there's a p-value percent chance of getting the sample results, in this case a p-bar, this extreme or different from the HO. I guess we could say if HO is true. That's what it is, okay? So that's the definition of a p-value. Let's go back and just take a look at that in terms of right at the very beginning of this unit. So we were talking about the nicotine example here, and we ended up with a p-value here then of, I think we did that down here. Yeah, here it is. Of somewhere between 0.5% and 1%. So we're saying that there's less than a 1% chance of getting these sample results if HO is true, if we are meeting the standard of 1.6 milligrams of nicotine. And so that means that we're likely not meeting the standard there. So we reject HO. So that's what we have here then, and that leaves us with one more problem that I'd like you to do for homework. Number 8, that'll take us to the end. There's a bunch of additional problems at the very end here, which you should be working on. Here's the solutions for them.